What do you know? That's right. 50%. Wow.
Okay, good. So I got some folks at home as well, which is super. I got Amelie, I got Lauren, I got Linus. Let me write you down. Thank you, Amelie. Thanks for being there. Lauren, Linus, Malta, be right with you. And Julius, thanks all of you for joining me. Yeah. Okay, and there's figures. Yep, sounds good. Okay. All right, Leon, I'm missing? He's not here. Okay. Let's see. Liam. And I also got online, I got Timothy P.
Oh, the form.
And I got, yep, I got you, Timothy, and I got you, Kiara. Thanks for joining me. Okay, so here's what's up. We're at different spots, my two different courses. So I'm going to show you pretty much everybody some new stuff today on electromagnetism. Am I right? This group, we only finished up optics last time I physically saw you. Is that right? And you weren't there either. So hopefully you got notes from somebody at least on optics of them. If you didn't, you need to do that. So, but I wouldn't copy those now. I want you paying attention. Okay? Okay. But okay. Good. And if you've got, as Alessia does, the sheet for permission to live stream, I would like that. If you don't have it, or if you're at home, could you please, the parental consent form, could you upload it, as many of you have done already, to Google Classroom for me? So take a picture, upload it, and then we're all set. Okay? Got another one?
I uploaded.
You did, then you're probably all set anyway, but I'll take it, that's fine. So let me just read off. There's, let's see here. So I still need a number of you to do that. So I think I still need, but I haven't looked today. I still need. You did yesterday? Okay, then I won't even say the names because I haven't looked at recently. Okay, Ninja's here. And not here, not here. Got anybody else? Yes, I do. I got a Charlotte. Good. Thank you, Charlotte, for checking in. Super. Thanks, everybody, for joining me. Okay, I'm going to go get the cart that has all of our stuff on it, and I'll be right here, and then we'll start doing some demos today. It'll be some new stuff for those that are joining me at home, okay? All right, so here we go. Hang tight for a sec. I'm counting on because I don't have to know what they were. Oh, it feels funny, like, you know,
Maybe on one.
No, not really.
Going to school.
Positive. You're such a small looking boy. Oh, God. I'm sorry.
Okay, I've got all sorts of stuff here, including a couple of power strips that I need because common source of electricity is pretty far from me, which is way over here. Unplugged some here, and we use two power strips.
Don't ever put water in my room. I did it before. I put something in my room.
Okay, I want to start with a review that I think some of you have done also. And let's just remind you of some stuff. I want to show you this. And when I do this with a rod, either folks at home or folks here, what am I doing to the rod, so to speak? What am I doing when I do this, Corey? I'm charging it. So I'm going to put some charge on this machine called an electroscope. So it's accepted some charge. And this turns out as negative charge. I don't expect you to remember that, but with fur on a rubber rod, that's negative charge. So what I'll do now is the opposite. And I'm going to put on some positive charge onto this one. And when I touch, why does it go down? Well, not completely, but why does it go down a bit? Try to put a little more on. Why would it go down, Ingrid?
It's positively charged now, like the rock.
The rod is, but what happens when I touch this? There was negative on this machine, and Tim?
Positive be overloaded. Or like.
Yeah, but you're making.
More protons.
No. Okay, okay, you guys are making it way too hard. So initially here, I'm going to ground it, as we say, to make it so it's got no charge. And I'm going to put on some negative charge. And folks at home can see that as well. What happens when I put on some positive charge? All right, Jake.
Electrons.
Yeah, and what happens? Why does this go back to like almost to zero? It should go to zero perfectly.
Because all the electrons are
Yeah, and in general, what? I had negative on there and I add to that, what? Positive. What happens with positive and negative? It's like math class, correct? Yeah, okay, they probably did. But I mean, what also happens? What if I add positives and negatives? What happens in math class? Yeah, okay, well, it makes zero in math class, but okay, here, I get a neutral charge, okay? Especially if I grab it, then any extra electrons go through me. So just like in chemistry, we talked about moving electrons around. That same thing happens in physics, doesn't it? Okay, now, and I've got some answers here from folks at home. And yes, the negative charge gets eliminated because they balance, the two charges balance each other out. Yes, Kiara, that is it indeed. Okay, so that's a bit about charge. Then I got, one other thing I want to show you. Yeah. Let's take some little bits of paper. Okay. And if I charge up the rod, why is it attracted? Whoa, without even touching, some of those papers are attracted here. What are they feeling, even if we can't see it? What are they feeling that's around this rod? What do you think, Evan? What are they feeling, even though we can't see it? Alessia,
The electron,
Yain,
negative is negatively charged,
right?
and so positively charged pieces of paper
Yeah, or at least neutral. They're attracted to
are attracted to the negatively charged rod.
Yeah, but what's around here, as we say in physics, that I can't see? I'm looking for another term for that. Zach. Yain, Abram,
Magnetic.
not magnetic. No, this is not a magnet. This is not a magnet, Tim. No, now we're just guessing. It's at home. What is it? Okay, what have I created around this rod? Yain. Okay, it's called an electrical field. A field. Okay? So even though I can't see it, it's there. I've got evidence of it because I can lift up things that are neutral and they're attracted to that field. Okay? So with electrical stuff, and I'm gonna write a little bit of this. That's a big mess. Who left that? So for electricity, I've got an electrical field. And I want to do something I didn't do with my folks at home. Let's make it so they can see. Linus knew that, so did Kiara. Good job, folks at home. So electrical field, let's do some field lines. Here's how you do that. Folks at home have not had this either. If I have something negative, and turns out field lines are where an imaginary little charge that's positive moves. So I can imagine a positive moving from any direction towards this, like that. And if I have something over here that's positively charged, what will happen if I put a little positive over by that one? And if I put a positive by a positive, which way will it go? It'll repel. So I'm going to show that by showing some arrows going the other way. And those are the field lines for a positive charge. So field lines in physics are where a positive charge goes. And I better be careful. Electric field lines. As you're catching up, I just want to remind folks at home and everybody, electricity and magnetism are two different things. And it's easy if we don't have these very often, how electricity and magnetism affect each other with lots of different demonstrations. And what that does for our society, there's two big applications that really help you and I, do all sorts of things in our world because of electricity. And you know what? I'm guessing you can't see so well with the glare. Jake, if you want to move behind Tim, that would be really probably better. I think you're going to see better there. Okay. Okie dokie. I'm going to try and get as little glare for these guys as I can. Okay. People at home, can you see that okay? Can you see that board okay? So there's an electrical field. Okay. Now, let's take these guys. Okay. What if I put, Corey, what if I put these two together? What's going to happen? So this time we don't have positive and negative. What do we say to the folks at home? Folks at home, we don't have positive or negative. We have for magnets. Let's see if somebody at home remembers too. Instead of positive and negative, what do we say about magnets? What do we say? North and south. So it's like the earth, isn't it? Because the Earth also has a field, not an electric field or what? Tim? Magnetic field. So Earth has one also, because it has metal in the middle of it, by the way. At any rate, so this has a magnetic field around it, and Malta knew that, as did Kiara. Good job. Keep participating, folks at home, so I know you're there, and all is well. I want to draw that field, and these guys at home have also not done this. It's called magnetic field lines. Magnetic field lines. I'm going to draw my magnet, kind of like I'm holding it. It's got one side that's red, one side green. So I'll just do like that, and like that. One side's north, one side's south. I don't know which is which. I'll just make something up. Let's say that's south, and that's north. So no plus or minus, but we do have north and south. Okay. The field lines are also around there. Like, Claire, let me ask you something. Here, I'm going to put let's say these are both south. I'm going to have the south here next to the south and here. How are they going to feel about each other? Yes, that's what they are. What are they going to do? They're going to rebel. And they do. She's right. So they feel the field of the other, even though I can't see it. They definitely can feel that. I can't put them together. They move almost like magic, right? We can't see it, but it's there. So that's the magnetic field around those guys. And I'm going to draw them around here. In magnetism, we say the arrows go from the north to the south. And if we analyze that, we find this. They go in these big loops from north to south. Or we can have lines going in like this, or out like this as well. So magnets can have fields, and also negatively or positively charged objects can have fields. So I got two different sorts of fields, don't I? Folks at home have had this, but I'll ask everybody. What's the big difference already you notice, or maybe you know, between magnetism and electricity? It's a big difference. Tim, what do you notice?
Well, magnetism is like a cycle. Again, like electrical fields are just like one-sided, some only repel or again.
Okay, you're really on the right track. It's sort of a cycle because how many parts do I have in a magnet? Two. Here it's a pretty simple pattern because how many parts do I have with an electrical charge? Ever? Just one. So here's my point. I can have something, and some of you knew that at home too, I'm guessing too. Yeah, right. Thank you, Kiara. Okay, so I can have something charged positive or negative, but with a magnet, turns out even if I break this thing, the parts I make, if I cut it in two, each of those has a north and south. I can't have a north without a south. I can't have a south without a north. But as you know from last semester, I can definitely have things that can be either positive or negative. Think like CO minus or Na plus. I can have separate items that have ultimately a charge, can't I? We know that from chemistry. So that is an important difference. And you can just say on the side here, aha. Magnetic fields always have north and south. North and south. Okay, and as you're catching up there, let me get something new for everybody. Oh, by the way, this is kind of cool. There's a magnetic field for you. If I put the magnet on this bunch of little tiny iron arrows, you can actually see the field. I know folks at home saw this already, but that's kind of fun. You can see which way the arrows actually go. Most of it. So you can see the field even though normally you can't see it. Here's the field in our little diamond.
Anyway, see the field from outside.
Yeah, have you ever done this, Abba? Maybe in elementary, where they had to sprinkle iron filings, and you can see that where the field would be. You can do that same thing here. I could sprinkle little bits of iron. I probably wouldn't want to put it on mine because it'd be a big mess. But I could put it under, and then it would sort of also line up with that. Yeah. Good. So let's get to our goal for the day. Where did I put it down here? All right, so folks at home, you have not seen this. So I'm going to describe it carefully for everyone, and we're going to draw it as well. I got a power source like you might have used in 8th grade for circuits. That's nothing new. I've got, oh, what are these called, folks at home? We don't really call them wires. In German, it's Kabel. But what is it in English? I've got one of these attached here. See if you can type in what that's called in English. I think you had it today. While you're doing that, I'm going to try and get into my power strips. It worked. Good. Make sure that's off. Yeah. Okay. Leads. Thank you very much, Kiara. Great. So I got one lead, and I'm going to do something that's going to look weird. I did some with folks here last week that was similar. I'm going to put it in one side and have it not go through a light bulb or anything, and I'm going to put it into the other side. So it's just making one big circle. Okay, that's all it's doing. And folks who are here, we haven't done this, right? Okay, just to verify. Let me get my little piece of paper out of the way. Okay. Good. We're going to look at an interaction here with electricity. I'm going to turn this on in a little bit. And a magnetic field. Oh, let me put this together. Oh, there it is. No, it's not. Come on. There we go. Okay, I'm going to show folks at home what I'm holding in my hand. Maybe they can guess what that is. And folks here now, you can probably see and guess what that is. One person knows, another, and a couple more as well. What is this thing? That? A compass. Good. Which way, Jake, which way is it going to point? North. Now, all of you point. Folks at home, you can do your own pointing. Which way is north? Think North Berlin. From here is kind of which direction? Everybody, can everybody point? Think of where Teltow is, right? Because that's south. Okay, good. So it's more or less this way. So most of you got it. Teltow is kind of that way. That's more south. So it's up this way. So I'm going to put this on the desk. And I'm going to make sure my folks at home can see this thing. There they can. And it's pointing about this way. It may be a little off. That's about right. Okay, so for me, the silver arrow, this one right here is pointing north, and the other one is pointing south. Okay, and it's stopping. And again, it's doing that because the has a magnetic field. The has a magnetic field. Stella? So what? Where's that field coming from? Alessia? Yeah, it's pointing a certain way because the has a magnetic field.
The magnet? The compass?
Well, look, now the compass doesn't have a field itself. What's it, Timothy? The planet, Earth, has a magnetic field. So not every planet has that, by the way. Most planets do not. So the Earth's kind of lucky it has one, but we'll go into that another name. Aha, got a newcomer here. Allie, you're mighty late. You're gonna have to watch the rest on video. Okay, here we go. What I'm gonna do is I'm gonna put this, hopefully where everybody can see. And hopefully where all of you can see. And what I'd like all of you to do who are here is, and Alessia, you may have to move up entirely. I want you to stand or get somewhere where you can see this arrow, this silver end of this thing. So feel free to come a little closer behind me too if you want. Or there, that's fine too. Okay, can everybody see that? Okay, good. What I'm gonna do is, make sure folks at home can see that as well. I'm gonna turn on the power. And I'm gonna turn it up and then back down. And we'll see what this thing does. You can see a little bit of movement when I do that, can't you? Just a tiny bit. I'm gonna turn up so I have even more what? What do you suppose I'm adding more when I turn this up? More, Jake? More charge flowing? What's that called? Charge flowing? I got a higher in my thing. Alessia? Voltage, Diane, probably the other one. What's the other unit in electricity? Voltage or Alessia? Because you had it with me last year. Voltage or, no, not watt. Watt is power. I'm not increasing the power. Starts with a C, rhymes with urgent. Okay, so current, and Kiara says amps, and she's right. So I'm increasing the amperes, right? The amount of current in amperes. Okay, you ready? So watch this sucker. And now you can really see it. If I turn it and then turn it off, it comes back. And if I kind of catch it at the right moment, you know what I'm saying? So I can really make this needle move. Well, first off, when I turn it on, what's moving in the wire? I can't see it, but what's probably moving inside the wire? Where current? Yeah, and physically, what is that then? Current's moving, yes, and what is current? What's really moving in there? Current. No, energy doesn't. I mean, a thing. What thing's moving, Ingrid? Electrons. So current means I got electrons moving, and when I do this, I make a move in one direction. So they go, suddenly they go, and they all get pulled one way. Okay? Well, when I pull them this way, suddenly this magnetic field is disrupted that's sitting next to it. So somehow, when I pull the electrons, yes, Linus had that SDKR, thank you. When I pull the electrons through the wire, it must make its own little to screw up the magnetic field here. It makes its own magnetic field, Tim, exactly. I'm going to make the effect even greater. I'm going to turn up to the highest voltage, or highest current, highest amount of amps. And I'm going to show this, and again, I hope everybody at home can see it as well. I can really get it to move. In fact, if I really hit it a lot, and what if I could do this? What about halfway through if I could turn this thing around? I'm going to show you something. Okay, when I do this, who can kind of see up close? When I do this, am I pushing or pulling the wire? Sorry, am I pushing or pulling the needle when I increase the current like this? What does that do to the silver part? I'm pushing it. Okay, so Zach's close enough so you can see and understand. So it's pushing it away. What do you think will happen, everybody at home too, if I turn the loop around upside down? What do you think is going to go on? Stella? Let's try it and see. She says it's gonna pull it now. And she's right. So now suddenly I pull it my way quite a bit. If I increase the current just at the right time, can't I? You ever push a little kid on a swing? And can I get him pretty high if I hit him right at the right time? That's what I'm doing here, aren't I? What if I could make this, I pull it, and then what if I could make it, ready? I'm gonna pull it. Whoops. Let's start again. Okay, I'm gonna pull it and pull it again like a kid on a swing. Pull it. And again. Look how much it's going. Eventually, what could I maybe do, especially if I turned it around at the other point and like pulled it from the other side? What could I do with this needle? Ultimately, I could, Ingrid, I can make it go all the way around. What do we call that in like skateboarding? I can make it do 360s. So now I want you to think about that. And if I have it do like 360s, if I can do that, now I want you to imagine, what good is that? What can I use that for? What is that as a society? Why? What sort of things do 360 that we actually use in our world? So let's pull out some ideas. So let's see.
Like record players, bands.
Yeah.
Yeah, like
Good.
basically everything that we
Yeah,
use.
a lot of stuff. So if I have a record player, an old-fashioned or CD player, if I have a fan, right, that goes around like we need on a warm day, which we might actually get sometime. What else goes around? What other sort of things, Jay? A clock. What else goes around? Windmills, although that actually makes electricity. They do go around, you're right, Corey. But for us, luckily, they make electricity. They don't take it. They don't take it. Washing machine, that's a good example. Yeah, although the Earth has not got one of these in it, though. The Earth moves for some other reasons, Efren.
A film tape. Like in the old movies.
Like in the old movies, okay? Yeah, yeah. There's something you guys often used to use when we were able to do this, to go to another country, and then something that also did this. All right, the old-fashioned ones did, not the new ones.
Planes, different
Planes.
colors.
Yeah, so old-fashioned planes
And
with propellers.
Also old fashioned, also new fashioned, feeders.
Yeah, beaters. Even in the kitchen, if you've got something that does this, you've got inside of it. So what is inside all of these things that makes something move around in a circle? And we're going to see how it's related to this. What's inside all of these things? No, it doesn't have a magnet. I take it back. It has, yeah, okay, there's a magnet in it. Yes, there is. But that's not the whole device. I want the name of the whole device that makes something go in a circle like this. Or makes something like in your washing machine go in a circle. Or, let's see if somebody else guessed it here. Yeah, 360. Okay, I don't know who this person is. You need to identify yourself or I got to kick you out. So say who you are, Nick Gar, or you're gone. Okay? It's called the motor effect. So it's in a motor. It's an electric motor. And I wish you could, Alan, can you pop it open with a chair for me? Thank you. Thank you much. Appreciate it. Okay, so let's write some of this down.
Yeah.
It's called the motor effect. And I'm going to move this up so now my folks here can see. And I got someone not identified, so they're gone. Okay. First, I want to draw this with you. So here was my compass needle. And I'll just draw north, south, oops, I went out a little bit. There's the middle. And then I'll draw my wire. So I have this loop of wire here. And that went to my power source. So I got a power source and when I turn this up, turn up current. What happened? The first thing we saw was what? Before Stella I flipped it around with her. Which way did it move when I first turned it up? Tim? Away. So I'm going to show that like this. And now let's describe a little bit up above. Okay, this may be hard to read for folks at home, so I'm going to say it as well. Okay, so with this loop of wire, we're going to call that our lead. That's what this thing was called. It's our lead. When current changes in the lead, a is created, which disrupted the of the compass. Whoa, okay, let's get a fill in some blanks here too. Okay, so when the current changes in the lead, there's the lead. And remember the current we said is electrons going back and forth, isn't it? So I can make, you guys should do it up here. Here's some electrons. E minus. But so we go like that. When the current changes in the lead, who is created, and I think we figured that out. What must have been created then? Claire, you got it. And I know it seems like magic, but it's not. It does that every time when electrical charges move like this, like little electrons, they create a field. And I don't want it to be magic. We saw evidence of it, didn't we? We saw that it disrupted the of the compass. The Alessia?
The motor effect? The circulation?
Well, it wasn't moving anywhere before that, so it must have disrupted the magnetic field of the compass. So what I'm saying is, Alessia, we know we made a magnetic field because the other one was disrupted by it. So which disrupted from Tim here, the magnetic field of the compass. Let's see if I got any questions here from folks at home. Notice your little instant replay, also for folks at home. Make sure they can see this. I still got on the maximum current. If I just turn it up, it doesn't go back and forth. It just repels and then it stays there. So if I really want to make it move back and forth or even rotate and make a 360, I've got to keep doing what with this current? I got to do what? I got to turn it on and off, don't I? I got to change it on and off. Now, what I did was do exactly that and then turn it on and off. If there was some way I could, what if I could change it from positive or from negative going to positive and then positive to negative? What if I could change the poles? the electrical poles. If I could do that, then I could really make it go like this and make it do like a 360 all the time. And that's kind of what really happens with real magnets. It's called alternating current. And we'll see how that forms too. Some of my students have gotten that already. Exactly, good. Kiara says turning the current higher and or lower. So back to what I wrote, that's why I really wrote when current changes. And by changes, we can write what Kiara said, either higher or lower. So made higher, that sounds kind of bad. Made greater? No, that sounds even worse. How about we say increased or decreased? That's better English. So when the current is increased or decreased, that's when I get a magnetic field created, which disrupts the one that's already there and can make that thing spin. And if I could make it go 360 degrees around, think now motor turning, something turning that we want to turn to make one of the devices that you guys said earlier.
Did Michael Faraday make an important discovery that has to do with this? Motor effect?
That I don't know. Michael Faraday did some pretty important discoveries with the other effect we're going to study. The group the other ones had last week called the generator effect.
Yeah.
He might have done stuff with the motor effect, but you may know more about that than I do. I know mainly what he did with the generator. And we're going to take a look at that. If we don't get to that today, Alessia, we'll get to that the next time I see you, which is tomorrow for you guys. Good. So we'll get to it tomorrow if we don't get it to today. Jump.
When you put the wire over the needle.
Yeah.
How do you, or like, it's like always the, I guess like, right, part of the cable is negative one? Or like.
How do I know that?
Yeah.
Okay, let me show you. What we haven't talked about, I'll show folks at home too, is what I got it hooked up, it says minus and plus here. And this is what's called a direct current. So it's going to go from the minus towards the plus, which makes sense, right? Because what do we say is moving through the lead? What do we say is moving? Yeah, and what little things is that? Electrons. So it makes sense they should be going towards which charge, Stella, the electrons? Towards the positive. So that's how I know, Tim. So they're moving from the positive to the negative. And so if I hold them a certain way, I know which way they're flowing in the wire. We haven't talked about that yet. There's actually special rules that have to do with that I won't have you memorize. But you can actually tell from the direction of the movement which way the thing's going to go ahead of time, if it's going to repel the needle or attract it. And just instant replay from what I did earlier with Stella, if I have it repel on one side, so I push that needle away, I can flip it around, or the other thing I could do is do what with these two ends, Tim? Switch them. All right, and now let's see. Sure enough, now it attracts. Yep. So it really does work in that way as well. Yeah, exactly. Good. Huge, super. Okay, so that's the motor effect. And let's put a couple examples before we go. Frankly, it's used in things that turn. Okay. So think of like a what? A washing machine? A car? What's some other ones we mentioned that I've already forgotten?
A boat. A boat. It's like the slant thing, like a boat.
A boat.
A boat. Like on the water.
Like the
A
motor?
boat. You mean like a motor for a boat? Yeah, sure. A boat motor. Yeah. just with the mask of them, it's so hard to hear, and my ears are pretty crappy anyway. Good, anything else that we said that I forgot to write down? Some other things that are turners? Planes, like the propellers in a plane. Plane propellers. Cool. And Alyssa, you had one more too.
Record player and film tape.
Film tape, I'm gonna write, can I write CD player?
Yeah.
Just to be somewhat more updated. Good. Because that spins something too, doesn't it? Yeah, good. Oh, man. Okay, time flies. Thanks everybody at home. Thanks everybody here. Will you put the chairs up before you go? And I'll say farewell to those here. I'm gonna read the comments here before I go. No, Kiara, they all move at the same rate. They won't move closer to here. They all move at the same rate. They can't move any different speed. Okay. Thanks everybody. Bye-bye. Bye-bye. Have a good night. We'll see you guys tomorrow.